The next point is important on the competitive exam point of view. So let us say we have an example that we need to find the total number of electrons occupied in an orbital. So if we have the value of n is equal to 3, so if anybody asks you, directly tell how many electrons can be accommodated for value of n is equal to 3. So you have simple formula, that is 2n square. This means to say how many electrons are there for n is equal to 3. 2 into 3 square, then we have 2 into 9 is equal to 18. Again, for n is equal to 4, we have 2 into 4 square, that is 2 into 16, and we have 32 electrons for n is equal to 4. So, if we are given value of L, so this formula can further be elaborated, is equal to sigma L is equal to 0 to n minus 1 2 into 2L plus 1. Let us take example for n is equal to 3. We will calculate using the L values. Okay. For n is equal to 3, L values are 0, 1, 2. So we will go on adding, putting the value of L in this formula and adding, because here the sigma sign is. So for L is equal to 0, we have 2 into 0 plus 1 plus 2 into, let me put it like this, 2 into 1 plus 1 plus 2, 2 into 2 plus 1. Here, this is the value of L0, L1, L2, and all the values are set according to this formula and then added subsequently. Now let us calculate. This is 0, 0 plus 1, 1 into 2 is equal to 2, plus 2 into 3, plus 2 into 5, we have 2 plus 6 plus 10, which is again equal to 18, which is equal to this value. So what is the meaning of this 2, 6, 10? If you see it clearly, then 2 represents the s orbital, which contains 2 electrons. This represents the p orbital, which contains 6 electrons. This represents the d orbital, which contains 10 electrons. So we have 2 plus 6 plus 10 is equal to 18. We can take another example for n is equal to 4. For n is equal to 4, let me write here. For n is equal to 4, value of L is 0, 1, 2, 3. So up to this number we have already calculated, which is 2 plus 6 plus 10. Now we need to calculate this additional number. So according to the formula, 2 into 14. 14, this number comes out to be 24, then we have 32. So again, if I say 2n square, 2 into 4 square, again these numbers are equal. So if you are given the value of L or N, you can directly find out the total number of electrons which can be accommodated in that particular shell or subshell. Okay, let me elaborate this formula in a little bit more details. This represents the total number of ml values. Okay, I have already explained that for each ml value there are two ms values, so that's why each value of ml is multiplied by 2. So this represents the two values of ms, which are plus half or minus half. So now another question comes, if this is 1s orbital, if this is 2s orbital, if this is 2p orbital. So we have already explained that it can contain 2 electrons, it can also contain 2 electrons, it can contain 6 electrons. So here, first of all, the question appears why these arrows in opposite directions. So the simple question is according to the Pauli exclusion principle, which says that one state can accommodate 2 fermions and those fermions should have opposite spin. So that's why one electron has up spin, other has down spin, and these arrows are represented in numbers plus half or minus half. Okay, so the second question appears that if we have let us say we have total number of 6 electrons, then how to arrange these electrons? We can write like this. We can write like this, or we can write like this, or we can write like this. There are so many configurations we can make, but the question appears, is there any specific rule according to which we can accommodate electrons according to that particular rule? So this is the Hund's rule. There are 2 points. Let us discuss the first point. Let me read it. One electron is placed in all the degenerate orbitals such as px, py, pz before a second electron is placed in any one of them. So in this point we need to understand 2 things: degenerate px, py, pz. In simple words, we have degenerate state. The states having same energy are called degenerate states. It means to say, if we have p orbital, we have 3 degenerate states: px, py, pz. Let me write here. This is, let us say, 2p orbital. So these orbitals can be divided into 3 degenerate states: px, py, pz. So these are the values. This is the total L value, and these are the values of Mn. So for P, L is equal to 1, Ml is equal to plus 1, 0, minus 1. We can write it like here: minus 1, 0, plus 1. These are the value of Ml. Similarly, for D, 1, 2, 3, 4 and 5. Let us say 3D. Let me put is 3. 3D. For D, L is equal to 2, M is equal to -2, -1, 0, +1, +2. So these are all degenerate states. -2, -1, 0, +1, +2, and the names are like this: dxy, dyz, xz, x square minus y square, z square. These things come from the quantum mechanics theoretical derivations. We need not to go in those details. So let us read the point number 1 again. One electron is placed in all the degenerate orbitals such as px, py, pz before a second electron is placed in any one of them. If I have to place one electron in P, it will go in any one of them. Let us say it goes in Px. Okay. If I have to place second electron, it will go in either Py or Pz according to point number 1. Let us say the second electron goes to Py and the third electron goes to Pz. Now, in order to accommodate the fourth electron, we need to understand the point number 2. Let me read it. The electrons in singly occupied orbitals have parallel spins. These are all parallel spins. If I need to further put the electron will go in either of these three states but in anti-parallel direction. So the next one will go either one of these, this one, this. All these 6 electrons are accommodated. Similarly for the subshell we have, all the states will be occupied singly according to Hund's rule, then doubly but anti-parallel state. Okay, so why this is so? The simple answer is every system wants to remain in stable state, and for that it occupies the minimum energy. So the electron, in order to occupy minimum energy as well as in order to remain stable, it follows these types of rules. Let us move further. Now we are able to fill the electronic configuration. Here I can write the atomic number, this name of element, here electronic configuration. Okay, so atomic number, let me put it like this. Z 1, 2, 3, 4, 5, 6. Hydrogen, helium, lithium, beryllium, boron, carbon. So for Z is equal to 1, we have only one electron, it will go to 1s1. For helium we have 2 electrons, it will go to 1s2. So we have 1s2, 2s1. This is Hund's rule. -2, 2s2. Then we have 1s2, 2s2, 2p1, 2 becomes 5. This is again we have applied the Hund's rule for carbon. Again 1s2, 2s2, 2p2. I can write only this one like this. So we can go on like this. We can take another example of higher atomic number. Let us take Z is equal to 11. As you know, the atomic number 11, the element is sodium. The electronic configuration is 1s2, 2s2, 2p6, 3s1. Okay. We can take one more example. We have, let us say, 14. 14 is silicon, 1s2, 2s2, 2p6. Up to here we have 10 electrons. We are left with 4, 3s2, 3p2. Let me take the example of 3p5. For 3p5, we have 3, 4, 5, 17 chlorine. I have to take the example of chlorine. 1s2, 2s2, 2p6, 3s2. Then we have 3p5. The 17. Okay, right. Let me write this case like this for more clarity. Up to here we are fully filled. So, like this. So 3p5. We will apply the Hund's rule. 1, 2, 3. Then we have 4, and then we have 5. So this is all about the electronic structure of the atoms. So thank you, students. If you have any question, you can ask me in the comment. I will try to answer the questions.